o'clock, so let's get started. So we have only 2 weeks and a little bit left, so I'm starting to get a little sad for that, but we're going to start looking at some really cool stuff soon. So what we're going to do today is we're going to finish up intractability by talking about problems we can't even solve at all. Next week, I'm going to cancel these topics, and I'm just going to talk for that entire week about research and things that I like researching about. And the final week is going to be entirely presentations. So the way I'm going to set that up is the first day I'm going to talk for half the time, maybe a little bit more about research or some other topic I want to talk about. Then we'll have one presentation on Tuesday, 2 on Wednesday, and there are 5 presentations. 1 on Tuesday, 2 on Wednesday, 2 on Thursday. All right? So is there any brave soul who would want to do it on Tuesday? So before anyone answers, I could defer this to the people who aren't here. So I can make them the unfortunate people to go first.
That's tough.
But you can...
What's the date? Sorry.
So the first one is the 5th of July. Second day is the 6th, and the third day is the 7th.
My only reasoning for wanting to go first is because I thought, well, I'm not being compared to anyone immediately.
You said the bar as low as possible. If you want to volunteer, just shoot me an email.
Okay.
That I want to go first.
I don't want to make a decision when my partner's not here.
Okay. Yeah, that's true. That's true. Okay, so we can have you go first if you email me, and then I'll set up people for Wednesday and Thursday. And so as the schedule stands, what we'll have is assignment 6 and 7. I'll need to update these, but 6 and 7 are out, and those have a due date. The final exam, I'm still working on it. I'm hoping to get it out a little earlier than what I have here, so that you can start working on that. And I have some really cool problems. It should be a lot of fun to do. And so when everything's due, I don't have anything for the project due until after the presentations, which is the last Friday of the semester, which is the 8th. So that day you'll have the final due at midnight and everything for the project due at midnight as well. So are there any questions on the schedule? So I'll update this, I'll send an announcement, all that stuff, so that you can keep this for your record. All right, so let's see. So assignment 6 and 7 are out. I'm letting you know that I will have limited email availability over the weekend, and of course assignment 6 is unfortunately due over the weekend. So are there any questions about assignment 6 or 7? So just letting you know, 6 is classifying the 5 of these problems as being in P or NP, and a lot of questions about coloring graphs and the limitations on how fast we can do certain coloring problems. And then assignment 7 is 2 problems on doing reductions and actually implementing them in Python. So you'll do a reduction from KSAT, which is a K-CNF formula, and converting that to a 3CNF formula, and I have the reduction here. So you basically just follow the recipe for how to make the formula. And the second reduction we saw in class, converting an instance of directed Hamiltonian path and converting it to the undirected one. And we showed that reduction yesterday. And so you'll be given a network X digraph, and you'll output a network X graph, such that the digraph had a directed Hamiltonian path if and only if the outputted undirected graph had an undirected Hamiltonian path. It's a lot of words. Yeah. That's one of the unfortunate things of this field in theoretical computer science. You have really long descriptions for stuff. But anyway, so those are the 2 problems I want you to solve, and then there's some extra credit stuff. So any last minute questions on this? Okay. I'll try to answer any email over the weekend, but as I said, I'll have limited availability. So if you have any questions, try to email me or post on the Google group as soon as possible, so that if anyone else has a question, they may say, oh, that was the same question I had. Okay? So any questions before we get back to the material and finish up intractability? Okay. So we've been talking, of course, about intractability. We've been talking a lot about these two classes of problems, P and NP. So P is the set of problems for which we can compute the answer, whether maybe, say, a graph is connected, as an example, in polynomial time, which is quote-unquote efficient. And so we reasoned that we can also verify a possible solution, a candidate solution, or also called a certificate, in polynomial time, because we can just compute the answer, and that's the certificate itself, the computation steps. But we wanted to reason about, what if we dropped the requirement that we needed to actually solve the problem in polynomial time, and just had the requirement that we just verify that whether an answer is correct in polynomial time. And that ended up with the class called NP. And so what we wanted to figure out is, are P and NP the same? Or are they different? And that's the million-dollar question. No one knows the answer. And so we tried to reason about what problems would be a candidate for showing that these two things are different, because most people believe they really are different. And so what we wanted to figure out was, what was the hardest problem in NP? And the hard problem is, if it were efficiently computable, so in P, for instance, then everything else in NP is also in P, because it's the hardest problem in NP. So we realized that if we can do a reduction, which is basically transforming a problem into another problem. So this hardest problem can be characterized as, every single problem in NP reduces to this really hard problem. And so what we wanted to figure out is there such a problem? And so we tried to figure out another way of characterizing it as, if we have two problems for which there's a reduction in both directions, then they both have polynomial time algorithms, or neither do. And so we looked at two problems, clique and independent set, for which they are polynomially equivalent to each other. And we showed the reductions for that. We also looked at vertex cover, which is another problem that's polynomially equivalent with these two. And so the first problem we looked at, which we didn't show the proof of, but we gave some intuition as to why this is true, of a problem that's NP complete, which is 3 satisfiability. So I have this conjunctive normal form formula. So I have a bunch of clauses which are ANDed together, and each clause is a disjunction of literals, so an OR of literals. So a literal is a variable or its negation. And so what we wanted to figure out is that if I wanted to show another problem to be NP complete, I didn't want to have to reduce from every problem in NP again, because it was a lot of work to do it for 3-sat in the first place. So we reasoned that if we just reduce from a known NP complete problem, then that would immediately show that it's NP hard. But if we also show that it's an NP, by definition that's NP complete, which is exactly what we want. So we just realized that, we didn't realize, but we came up with a transformation, a reduction from 3-sat to clique. We already showed that clique is in NP by letting the certificate, the candidate solution, being the set of k vertices, and I just need to check, is this an actual clique in the original graph? And it's pretty simple. But we showed that it's NP hard via reduction from 3-sat. And so the reduction is using these clause gadgets and hooking them up in a certain way, such that the original formula was satisfiable if and only if the output graph has a clique of a size of a number that I give it, which happened to be the number of clause gadgets. And so we reason now that since we showed that clique is NP hard and it's an NP, it's NP complete. But we also showed that independent set is NP complete because we have the polynomial time reduction from clique to independent set. and also to vertex cover. So we can chain these polynomial time reductions from one problem to another. Then we talked about another problem called Hamiltonian path, which was the main motivation for this, because we said that the longest path problem seems to be much harder than the shortest path problem. And so this is really the longest path problem. And we showed that was NP complete via a gadget proof. So we gave, I should fix this, variable gadgets and clause gadgets, and then hooked them up together, such that the original formula was satisfiable if and only if the graph had a Hamiltonian path at the end, which is exactly what we want. So, and then we also gave a reduction from the directed version of Hamiltonian path to the undirected version, because I may be interested in undirected graphs. And the reduction to the directed version from 3-set didn't work for undirected, so we wanted to model the direction of edges in the directed version as undirected edges in the undirected version. Okay, so that was quite a lot. So are there any questions before we move on? So now we get to look at something a little, it's kind of interesting. It's more practical and less practical at the same time. So more practical in the sense that it relates to problems that we care about a lot, but less practical in the sense that we don't have an algorithm to solve them. So it's kind of an interesting trade-off there. So we talked about NP-complete problems, a whole bunch of them actually, and NP-complete problems, like such as 3-set, are solvable in exponential time, right? So we have n variables, and what I can do is I can set all possible truth assignments to all n variables. So I have 2 choices for the first, 2 choices for the second, all the way to the 2 choices for the nth variable. And so what I can do is for each of those assignments, figure out the truth value of the formula, right? So if I figure out the truth value of the formula and any of them say true, then I know the formula is satisfiable, right? So 3-set is solvable in big O of 2 to the n times. So it's solvable in exponential time. But what we want to figure out is, are there even harder problems that take maybe doubly exponential time or triply exponential time or maybe factorial time, possibly? And it actually turns out that there are. So are there problems that are harder in a sense than NP-complete ones? And there are quite many of them. And so in what I'm going to talk about next week with regards to my research, I'm going to tell you about whether we can actually provably say that there are problems that are harder than NP-complete ones. Because maybe they take a long time, but we're just not clever enough to get them down to NP-complete level. And it turns out that there are, but I won't get there yet. So maybe we want to say, instead of the hardest problem in NP, maybe the hardest of all problems that exist, right? Just maybe the hardest one exists. Maybe there's some completeness result for it. But it kind of depends on what you mean by hardest here. So you can think of hardest as in 2 different ways. So the hardest of every single problem that could possibly exist, or maybe just the ones that we can actually solve at all, right? Because I don't prove it here, but maybe there are some problems that we cannot solve at all, right? They're just too hard to solve within a finite amount of time, given the size of the input. And so what we're going to do is we're going to consider, we're not going to really look at these in detail, but we're going to look at whether there are problems that don't fit into the second category, whether there are actually problems that are beyond a finite amount of time, which is would be kind of important, because for those problems we know that there's no algorithm to solve them, because an algorithm by definition runs in a finite amount of time, so there's no algorithm to solve it. So are there problems for which there's no known algorithm for, or even if it's not known, whether there's a provably no algorithm for it? Regardless of how clever we are, there's no algorithm to solve this. And so it turns out that most, and I'm going to define most in a second, most problems do not have algorithms. So, and that's actually quite disappointing, right? nearly every single problem you could possibly think of, there's no algorithm to solve it. And we'll see why in a second. So here's proof. So it comes from three really short exercises. So how many of you have seen the cardinality of the natural numbers versus the cardinality of the real numbers? Proof. Has anyone ever seen that? Okay, I can do a nice short proof in a bit, but it relies on that. So the natural numbers are the positive integers, 1, 2, 3, 4, the infinite set of positive integers. So I claim that the number of algorithms has the same cardinality as the natural numbers. And what do I mean by same cardinality? What I mean is the integer 1 corresponds to some algorithm. Number 2 corresponds to some algorithm. 3 to some algorithm. And there's no number that matches to 2 algorithms, and there's no number that matches to 0 algorithms. They match exactly 1 to 1. Okay? And so why is that true? Well, where do we store algorithms typically? Like if I'm not running an algorithm, what am I doing? Well, I'm saving it on my computer, right? Right. So how are algorithms, more generally anything on a computer, stored?
In main memory.
Well, in main memory as what? What is the fundamental? Yeah. So bytes are more generally bits. Yeah. So it's just a sequence of bits, right? So 0, 1, 1, 0, 1, a whole bunch of bits for each algorithm. And it's not hard to see that if I have 2 different sequences, no, another way to think about it is if you have 2 different algorithms implemented differently, then they'll have 2 different representations. They won't be the same representation, right? So it'll be a different sequences of zeros and ones because they're different algorithms. So you can think of each of these sequences of zeros and ones as a number. And so that's where it comes from. So that number corresponds to the number in the natural numbers. So therefore, the number of algorithms matches the is the same cardinality as the natural numbers because they match with the lights went out again. So they match up because it's basically the bit representation of the algorithm matches up with the number itself. And so what I want to be able to show now is that the number of problems that we want to solve have the same cardinality as the real numbers, which is much greater than the natural numbers. So why is that true? Well, I'll just do this as an example. So let's see. I don't want that. Let's zoom in. So let's think of all that. So let's think of all the possible instances of that could be provided to a program. So all possible inputs are just binary strings, right? Because everything can be converted to a binary string anyway. So just think of inputs as binary strings. And so these problems that we've been talking about are decision problems. So whether it says yes or no, right? So we can think of the inputs as 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1, etc. Right? So what is this set?
Set of all possible binary strings.
That's the way to think of it, but if I think of these as positive numbers, what is that?
All the natural numbers.
Natural numbers, well, including 0, but so this is equal to the natural numbers, which I'm going to call n.
I thought natural numbers included 0.
Some definitions do, some don't. But we can just include it here for convenience.
I know 0 is not included in integers.
No, it is. Yeah.
It is?
0 is an integer, yeah. Some definitions of natural numbers don't put zeros. Most do, though. So well, it'll be easier here, but it's a minor point. So we can think of a problem as a set of these, a subset of these binary strings. So maybe for a particular problem, let's see, like P1, it's going to say yes on 0, it's going to say no on 1, it's going to say yes on 0, 0, yes on 0, 1, not on 1, 0, not on 1, 1. It's going to basically be a subset of each of these, right? So problem 2 may have x, include x, x. It could have a whole bunch of possibilities. So you can think of this as, for an arbitrary program, I either include 0 or I don't. I either include 1 or I don't. Include 0, 0 or I don't. Right? So I have 2 possibilities for the first, 2 possibilities for the second, 2 possibilities for the third, and so on. But the problem is that this set isn't finite, right? So what is 2 to the number, 2 to the cardinality of the natural numbers? That's the cardinality of the real numbers. So this is in correspondence with the real numbers. So 2 to the power n, where n is the size of the natural numbers. So this isn't like ordinary math now. It's set theory stuff. 2 to the power of the size of the natural numbers, that's the size of the real numbers. And what we'll see in a second is that the natural numbers is much, much smaller than the size of the real numbers. And so let's think about what possible implications this has. So the number of algorithms has the same size as the natural numbers. You can think of it as the natural numbers. And the number of problems we want to solve as the size of the real numbers, which I claim is much, much bigger than the size of the natural numbers. So therefore, and this is a formal way to say it, so natural numbers are what are called countably infinite, and some people say that this is what is called listable in some order. Like the integers I can list in ascending order 0, 1, 2, 3, so I can list them in an order. But the reals, you can't do that. It's what's called uncountably infinite. And so therefore, there are more problems. So there must be some problems for which we don't have an algorithm to solve it, because they're much bigger than the set of algorithms for which we can use. All right? So therefore, there are some problems that don't have an algorithm to solve it. And so the only thing now I need to prove is that the size of the natural numbers is smaller than the size of the real numbers. Okay? So that's the only thing I need to prove. Any questions about any of that? Okay. So what I'm going to do is I'm not even going to prove that the size of the real numbers is uncountably infinite. I'm going to restrict it to between 0 and 1. Right? So which would be even a stronger statement, right? I don't even need to consider all of the real numbers. I just consider 0 through 1. Okay? So when I talked about the natural numbers, I said that they're listable in some order, right? So I can list out the natural numbers in some order. And so what I want to say is that the real numbers, I can't list them out in any order. In some order that I guarantee every single real number will be on that list somewhere. Okay? So what if I wanted to prove that this that I can't list them in some order? What would be a reasonable way to approach proving that? I claim that it has some property, but what would be a clever way that I can prove this? I want to prove that. Essentially the same thing, yeah. But one thing I can do is I can just claim that I could list them, right? And then I can say, oh, here's the listing. And then I can derive a contradiction. If I derive a contradiction, then my supposition that I could list them is false. So suppose that R is listable, or is countable. Is the correct term is countable. And so what I want to do is I want to list some sequence of numbers between 0 and 1, right? Because that's what I'm restricting myself to. So we can think of this as a binary string, starting with a period. So period I can just do an example. So period 0, 0, 1, 1, 0, 0, 0, 1, 0. Just a long binary string, right? And what I can do is, suppose that I had just this real number, which happens to be a rational number. I don't know what it is, but it terminates. But what I can do is, I can just I can add a whole bunch of zeros at the end. I'm going to add infinitely many zeros because it doesn't change the value of the number. So I'm just going to add infinitely many zeros after this. But maybe I have some irrational numbers. So maybe this one happens to be irrational. For instance, I don't know what it really is, but it's an infinite binary number. Maybe I have one more, maybe a few more. Yeah, I should do at least one more. So since I claimed that this set of real numbers between 0 and 1 is listable and countable, then, and this goes on infinitely, because I know there are infinitely many numbers. That's without proof. But what I want to claim is that I suppose that this list is countable. Right? So I suppose that every single number between 0 and 1 is on this list somewhere. Right? That's what I claim. Okay? So how can I prove a contradiction? Well, what I can do is, if I can generate a number that I guarantee is not on this list, then this list is not complete. Right? So therefore I have a contradiction. Any questions on what I'm trying to do? Yeah?
Are you trying to list those in order?
This is not in any order. I'm just saying there is some way to enumerate the real numbers. I don't care what the order is, and it actually doesn't matter what the order is here, but I just claim that there is some way to do so. Okay?
So you can just say it's one less than the lowest one.
It'll actually almost be this. So what I want to do is I want to make sure that I can make a number that I guarantee is in here. So if I do that, then I just found a number on this, now I just proved incomplete list, which will prove that my supposition is false. So therefore, I would be done. So how am I going to make a number that I guarantee is not on this list? Well, if the number, so each of these numbers is infinitely long. So I don't need to worry about truncating or anything. So if I want to guarantee a number not on this list, then it must differ from every other number by at least one bit. Right? It can't be the same for every single bit. There must be one bit that's different from every other number in the list. So what do? I start with the first number, and I choose. I'll just go down here. So I start with the first number. With the first digit, I make it the other digit. So if it was 0, I make it 1. If it was 1, I make it 0. So the first number starts with a 0, so I make it a 1. So it differs from the first number, so it can't be equal to the first. So now I go to the second number. Now I want to guarantee that it's different from the second number by at least one position. So which one do you think I'm going to change?
0.
Well, which position digit?
Second.
Second digit, yeah. So because I already wrote down one digit, I can't change that. So I'm going to change the second digit of the second number and write that down. And you think now third digit of the third number, I'm going to write that down. And then fourth digit of fourth number, and write that down, and continue through the entire list of numbers. Now, I just guarantee that this number is not on this list. So therefore, my supposition is false, because I just made this list now incomplete. I found a number that's not there. Okay? It's pretty slick on how it was able to prove this. And so one way you can think of this is that you can think of these binary strings as problems we want to solve. So like 0 could mean that I include the first string in that particular problem. Maybe 1 means I include that particular string in the problem. The binary strings as before. Okay? I know that it was a little different than what we've seen before, but does that make sense? Okay. Cool. So essentially now what we have shown is that there are some problems that we don't have an algorithm to solve. It didn't show me an algorithm it didn't show me a problem that didn't have an algorithm to solve it, but we know that they must exist, right? That's the essential takeaway from this. All right, so let's start on actually trying to get a particular problem that we know doesn't have an algorithm. So what is one? Do we know of one? So what these are called undecidable problems. So a decidable problem without the un means that I can solve it in a finite amount of time. So undecidable means that there is no algorithm to solve this problem. So what I want to do is I want to find an undecidable problem. And some examples. I'll just give some examples. I won't prove that these are undecidable, but for example, when we talked about context-free grammars for parsing a whole bunch of things, including programs for a programming language, determining whether a context-free grammar accepts every single string, that's an undecidable problem. There's no algorithm to solve this. Determine if a program will halt or not, right? That's a problem that we care about. Like, I'm sure everyone has written a program by accident that runs into an infinite loop. So maybe you may think, well, maybe there's some procedure that I can throw my program into and it tells me, will it run into an infinite loop or not? And it turns out no such program exists. There's no algorithm to solve it, provably. For any general program, there isn't such a thing, which is actually quite striking. We'll actually look at a different problem, which is called the acceptance problem. And I define this as accept. And what it is you are provided a program, and it doesn't have to be Python here, but it's just some sufficiently complicated program with input W. It doesn't matter what W is, and it outputs true. So when I feed W into this program, the output says true, or yes, or whatever you want to think of this as. If there's some output you want to measure, right? Maybe it returns 500, for instance. And so I'm taking an arbitrary program in and an arbitrary input to that program, and I want to figure out, does it say true when I run that program on that input? Okay? So that's the problem I want to solve. And so you can think of this as somewhat similar to this halting problem, this infinite loop problem, right? It actually turns out to be the same level of hardness as accept is, but I won't prove that here. And note that it actually doesn't have to be specific to Python, as long as it's what's called a Turing-complete language. So you're basically, I won't define it here, but it's a sufficiently high-level programming language, or like sufficiently capable programming language. But that's all I need. Okay? So any questions on the problem so far? So I want to show that this problem is undecidable. So there's no algorithm that will take a Python program and an input and tell me whether it outputs true on that input. Okay? Note that some people get confused by this and say, well, I can tell that this program will output true because it has a return true statement and there's no conditionals in it, for example. And that's fine and good, but note that accept has to work with every Python program that could possibly exist and every input that could exist. Okay? So it needs to work for every single one of those. And I'm claiming that there is no such way. It could work for some of them, right? It could work for some programs, but it can't work for all of them.
So this is without actually running the program then?
We'll see that in a second. Yeah, so a good idea is, why don't we just run the program on that input? And that's a sensible thing to do. But what's the problem? It could run forever, right? It may just stop and return true on sometimes, but sometimes it could run forever, right? So that's a problem. So it could run forever. So if we want to prove that there's no algorithm for this problem except, then maybe we're just not clever enough. But what we can do is similar to the proof for showing that the natural numbers are different from the real numbers by doing what is called a proof by contradiction. So I suppose that the opposite is true. So there is a algorithm for except. I assume that one exists. Okay? And then what I do is I develop a contradiction no matter what happens. Right? That's what I want to do. And if I drive a contradiction, then my supposition that there is an algorithm, it must be false. So therefore, it would have to be undecidable. So let's just suppose that one exists. So I say A will decide, which means that it's an algorithm for except. So A takes in this Python program and input and says, it will say true on this input, or it will not say true on this input. It'll say yes, or it'll say no, no matter what program or input is provided. I just assume it exists. Okay. Any doubts to any of this? Because this trips up some people quite frequently, so I just want to make sure we're on the same page. So except is undecidable. What we want to do is we can just make an algorithm B that uses algorithm A, right? Because I said algorithm A is an algorithm, obviously, so it runs in a finite amount of time. So if I use that algorithm A, then I can just make an algorithm B that also runs in a finite amount of time. That's perfectly logical. So I'm going to make a program, and what I want to do is I want to make B will always generate a contradiction. And what's my contradiction? By assuming A exists, I want to make sure that B cannot exist, no matter what. That program doesn't even exist. Like, it doesn't even run an infinite amount of time. It just doesn't exist, which is kind of weird, but we'll see how that is created in a second. So, and if we can prove that, then B cannot exist, which is exactly what we want, because the only way B could exist is based on our assumption that A existed, right? Because we're going to make B based off A, right? And if there's no way A could exist, then certainly B can't exist. So that's what we want to do. And that implies A can't exist. So the idea is, if we can make B simulate its own itself, basically its own code, then we can disagree with itself. Okay? This is what is called the recursion theorem, but don't worry about that. What we want to do is, if we simulate ourselves, we want to make sure that B accepts its own code if and only if it rejects its own code. It says yes to its own code if and only if it says no to its own code. That's a contradiction, right? It's pretty awesome, right? So that's essentially what we want to do. And so the main point here is that we need some ability to be able to access the source code of a particular program, which we can do by, in modern computers, by just saying open file of my own file name, for example. Like in some programming languages, they give you a special name, which is the name of the file that you're running. Like in Python, you can do that. Actually, many languages you can do that. And there are actually programs that are really interesting that are called quines. So how many of you have heard of a quine? Q-U-I-N-E. So what a quine is it's a program that when you run it, outputs exactly its own code without actually accessing its own code. So you can just say open the same file name and then just print its contents. I could do that, but I want a program that doesn't do that but still outputs exactly its own code exactly. No changes at all. And that's what is called quines. And there's actually a really cool GitHub page. I don't know what it's named exactly, but what it is there are 100 programming languages, and what they do is you start up one program, it outputs a program in the second language outputs one in the third outputs one in the fourth, all the way around. 99th outputs the 100th, a program in the 100th language. The 100th language outputs the exact same program in the first language. So it's like a circular quine, which is actually really cool, but I'll leave you to be able to look that up. It's actually really fascinating. But the key here is that we don't have to be a client. We can access our own source code if we want. That's totally allowed. And the whole point is that source code is a string. And we can think of an input to a program as a string, for example. Even if it takes multiple parameters, what we can do is separate them by some delimiter, maybe a pound sign, and then just string it together as a string. We can do that if we want. So we're going to think of inputs to a program as a string to a program. Okay? So how are we going to make B? So we assume that A decides this problem we want to solve except. So except, remember, is a Python program and an input W. So the way we're going to denote the source code of our program is with these angle brackets. So angle bracket P means the string, essentially, of the source code of program P. Okay? And so what we're going to do is we're going to run A on input the Python program itself, P, but we're going to feed the source code of P to itself. Okay? Just as a string. We can do that if we want to. And I assume A exists, so I'm free to make this program, even if it makes absolutely no sense to do this. Like, Ryan, why are you doing this? You can certainly do this if we want to. There's no limitation to this, assuming A exists. And then I return the opposite of whatever A says. So if A says yes, P accepts its own source code, whatever B returns will be no on input just this program P. Okay? And if A says no, P does not say true on input its own source code, then B is going to return true on this particular program. Okay? I can make this program. I assume that it's an algorithm based on the assumption that A is. So I'm free to make this thing. And so it's actually, this is from the theoretical textbook where it comes from. Don't be confused by the notion of running machine on its own, what is called descriptions. So these angle brackets are called descriptions. So it's actually nice that even a theoretical textbook is emphasizing the notion that a program can access its own source code, which I think is pretty interesting. Okay, so now what we're going to do is we're going to show that B cannot exist. So I mentioned earlier that we want to have a program B disagree with itself. So if we look at the program back, it's not really disagreeing with itself, right? It's disagreeing with what A says, right? So it's disagreeing with what A says. So A and B could be totally different things, right? Let's see. What does except mean again? What except means is that P will say true on its own source code. Okay? And B says the opposite thing. Or A says no, P does not accept its own source code, and B says the opposite thing. Let's run B on its own source code. Are we allowed to do that? Why not? Yeah, because we can just have a program load its own source code, and then we're all set and ready to go. So let's see. So if we run B on its source code, so instead of P now an arbitrary program, we're just running it on one program, which happens to be B. The same program so it's running as input its own description, its own source code. So let's see. We're going to substitute P for B now, right? Because that's where we're passing in as input. So we're trying to run this. So we're going to try to run A on input B with B's own source code and then disagree. So I just substituted P for B. That's all I did. So that doesn't immediately say that this is a contradiction. But let's try to understand this. So let's see. A can return true or false, right? So let's look at those two possibilities. So if A says true, that means B said true on its own source code by the first line of the program, the first line indented. B said true on its own source code. That's all what A is defined to mean, right? But what did B return? the outer program return? Well, it says return the opposite. So it returned false. So the outer program said B said false on its own source code. But here on the first line it said B said yes, said true on its own source code. So B said true on its source code, but also B says false on its own source code. Oh wait, that seems like a problem. Let's think of the other case. B says false on its source code from algorithm A. So A says false. B does not accept its own source code. Oh wait, it returns the opposite of what A said. So B then therefore returns true on its own source code. So B returns true on its own source code if and only if it says false on its own source code. Isn't that awesome? I just love that. So suppose it said true in its own source code, then B returns the opposite of what A said. So A said false. But this, by definition, means B does not say yes on its source code. It says no on its own source code. Or says it says false, for example. So that's a contradiction. If B says false on its own source code, then therefore B returns the opposite of what A said. So A said true on this, but by definition, that means B does not say false on its own source code, by the definition of A. So that's a contradiction. So B can't exist. Because B says true on something if and only if B says false on the same thing. So that can't possibly exist, right? So B can't exist, but by the logic before, that means that A can't exist. Because the only way B could be constructed is from A. So if A couldn't exist, so B can't exist. So therefore, A can't exist either. So therefore, there's no algorithm to solve this problem. I know it's a little convoluted in how the construction works, but are there any questions on that? You sort of got it?
Just a little bit, yeah.
Yeah. It warps people's brains a lot. I totally understand. But the notion is we want to simulate a program on its own source code and then disagree with itself. And the key here is that we're able to access our own source code. If we can't do that, then we can't prove it this way. But since we can access our own source code, then we're all set. It's because we can just feed B its own source code, and because we can construct B by assuming A, then we can just disagree with whatever B said on its own source code. So therefore, we can make a program disagree with itself.
One question though is A, does it basically just run whatever program it's included into it?
Yeah. So A is assumed to be an algorithm for this problem except, which takes in a Python program and an input, and it says this Python program will say true on this input. That's I assume it exists, right? And then what we try to do with B is we make a program that I assume A exists, so therefore I can make this program. And what we do is we try to simulate B on its own source code, and therefore we return the opposite of whatever it said. So we're making it disagree with itself. Okay?
It's like trying to return the Boolean value of this statement is false.
Right, yeah. There are a lot of logical inconsistencies with the English language. Like this isn't one, but this sentence disagrees with itself, or something like that. Like there are a lot of inconsistencies there, including in what is called Turing machines, which is basically what this is, being able to have programs disagree with whatever it said, and showing that an algorithm, not an algorithm, a problem is undecidable, so there's no algorithm for it based off of that. Okay? So, any questions on that? So, what I'm going to do is I'm going to finish up these slides and then we'll quit early today. So, you may think, well, we have one undecidable problem, and we did for NP completeness these reduction things that we got more undecidable problems, right? So, can we reason about reductions between undecidable problems? So when we came up with reductions, we wanted polytime reductions because we didn't want a reduction to be more powerful than the class itself. Because like for NP completeness, maybe I give you doubly exponential time to do the reduction. Well, I can just solve the problem anyway, doing the reduction. I want to make it less powerful. But for undecidable problems, any amount of finite amount of time will work. I don't need just polytime. I can do any amount of time I want. As long as you have what is called a computable function, and what that means is you can compute it in a finite amount of time. So if there's an algorithm to transform an undecidable problem into another one, then you're all set. You don't need just polytime. You can do any amount of time. So we use them differently here. We assume that an algorithm for the intended problem exists. So for NP completeness, we assume that both problems exist. We assume that algorithms for both problems exist. But here, we have to assume that the intended problem, there's an algorithm to solve that. And then what we do is we use that knowledge to make an algorithm for a known undecidable problem, which can exist because it's undecidable. So therefore, that would prove that this supposed algorithm cannot possibly exist. All right. Any questions on that? And so what we'll do one reduction, which is the halting problem. So this is the infinite loop kind of problem that we talked about before. So halt is essentially the same thing as accept, but now I just require you that you halt in a finite amount of time. I don't care what you return. I don't know what you say. All I care about is that you stop at some point. That's all I care about. And so that's essentially what the infinite loop problem is, the inverse of it. But it's related to accept. And so what we want to do is we suppose that an algorithm for halting exists, and then using that algorithm, we make one for accept. But we know one for accept cannot exist. So therefore, the algorithm for halt can't exist either, which is what we want to show. And then we want to make halt say true if and only if accept says true. So we want to preserve the yes and the no answer as we did with NP completeness. So the reduction is we're going to take, so here we want to make an algorithm B that will solve accept, assuming that the algorithm for halt accepts. So remember that accept takes a Python program and an input W. So this is basically we're making an algorithm for accept now. So A here is that halt problem that I want to show that is undecidable. So I run A on this input. And if A says false, that means that P does not halt on input W, right? So what does that mean for the original problem accept? So if it runs forever on input W, will it ever say true? Will it ever return true? No, it can't. So therefore, I say false, right? P can't return true on W because the algorithm that I suppose exists says it'll run forever. But it could say true, right? If it says true, we're going to keep going. If it says true, then that means that program P will halt on W. I don't know what it returns. I just assume now that A said true, so therefore it must halt and say something, right? So since we now know that it won't run forever, now I can just run it, right? Because we know it won't run forever. So if it says false, that means that P said false on W, obviously. So therefore, we return false, right? Because I want to solve the acceptance problem, right? We just showed that P does not say yes or true on W. But if it says true, then we return true, right? So let's think about this for a second. So I want to solve accept. So the only times I want to say true are when P says true on W. Those are the only times I want to. Well, the only time I say true is when P says true on it. In the other cases, it said false or it ran forever, right? So therefore, I just made an algorithm to solve except, right? But we know one can't exist because we just proved that one can't exist. So therefore, the only way that this could exist is if A existed, right? I know this is a little confusing, but in order for B to exist, A has to exist. So therefore, A can't exist because we know B can't exist. So A is the problem HALT that I want to solve, determining whether a program halts on an input, and therefore we just showed that it's undecidable. So just go through the proof again. So B is the problem except, so if it says true, then it can only happen at the very end, right? So A must have said true in the beginning. By definition of A, P halts on W because that's what A does. Since we return true, then P must have said true, right? So therefore, we must be correct in this part. In fact, we only say true whenever P says true on input W. What we do usually is if it runs forever, we say it implicitly says false. So it doesn't actually say true or false, but we say it implicitly says false. But that's a minor point. Therefore, we have solved the except problem, right? But we know that an algorithm for that can't exist because we just showed that no algorithm for it exists. So therefore, our supposition that HALT, there is an algorithm for it, can't possibly be true, so it's undecidable. Okay? Are there any questions about that? So I think this is getting close. Yeah, so 2 more slides, I promise. So we've talked a ton about untractability. We've talked about tractable, well, not so tractable algorithms, but they run in a finite amount of time. Algorithms, which are the NP-complete ones and the polynomial time ones. So just because one algorithm or one problem is efficient doesn't mean the opposite problem is efficient. Like when we talked about shortest paths, we know that's efficient, but the longest path problems we proved, it seems to be a lot harder. We don't know whether it really is harder because we don't know if P is different from NP, but we believe it to be harder, right? Just because one problem is easy doesn't mean the opposite quote-unquote problem is easy. But that's exactly the same one. Even similarly worded problems have very different difficulties, Dougherty. Nope, I don't have an example. So yeah, we have, like in your homework, one of the problems that is easy to solve is 2-color, but 3-color happens to be NP-complete. So even there varies a slight difference in the problem description, but they're vastly different in the amount of time needed to solve them, we believe. All these problems are easy or difficult because all NP-complete problems have polytime algorithms or none of them do because of these polytime reductions between them. No known polytime algorithm for any NP-complete problem is known. And if you are able to find one, then you'll be extremely famous. But we believe no polytime algorithm is going to exist in the size of the input. And even if determining the yes answer is easy, the no answer may be difficult. So, and vice versa. So, an example of where the no answer is easy, where the yes answer is hard, maybe like, for example, like a 3-sat formula. A 3-sat formula is what is called a tautology. If every single possible input I can provide to the variables makes it true. So there's no way I can make the formula false, right? So what would be an easy way for me to verify whether the formula isn't satisfiable for some input? What I can do is I can get the certificate for a possible setting of variables to make it false, and then I just verify it, right? So I can, in the size of the number of variables, I can check whether the formula is true. Whether the formula happens to be false on that particular input, and that would show that it's not a tautology. But the yes answer seems to be much harder here. So to determine that tautology is that a formula is a tautology, I need to I need to check every single possible setting, which could take exponential time. So linear time for checking the no answer, but seemingly to be exponential time for the yes answer. So it seems that even though one answer may be easy, the other one may be hard. But for polynomial time computable algorithms, I can just invert the answer. I'll leave that as an exercise. But for NP, we don't know whether NP versus what is called co-NP, which is the set of problems that are the opposite of the NP problems. We don't know if they're the same or not. So for the undecidable problems, even though problems may be deceptively simple or they have really easy descriptions like the accept problem or the halt problem, it may be not possible to solve it, right? They may even have really long descriptions of English descriptions of the problem, but they may be really easy to solve, right? So the length of the description or the seeming hardness of the problem doesn't actually dictate how hard the problem is. So even problems we care about, we talked about two of them, detecting infinite loops or determining some return value of a program, there may be no algorithm for it at all in general. There are some algorithms that can work for some set of programs if you assume something else about the program, but not in general. And the thing here is that we didn't conjecture anything, right? We're not just saying, oh, it may run infinitely long on some inputs. We actually proved that some algorithms can exist, which is actually pretty nice. Like for NP completeness, we proved that the reductions actually did work, and here we showed that some algorithms can exist. So it's really nice to be able to say, these problems really are difficult. For the NP complete ones, we don't know if they are hard yet, but we believe they are. So it's nice to get at least some conjectural evidence for it, some empirical evidence to show that these problems are hard. In fact, I won't show it here, but there are hierarchies of undecidable problems. So there are some problems that are just undecidable by themselves, and then there's a whole nother level of undecidable that are undecidable relative to the first level, then a third level, and there's actually infinite levels of hierarchies here, but I won't show that here. And that's it. So references from Sipser's book for the hand path pictures, but that's it. Any questions about any of this? I know that was a lot, so just letting you know, since I'm going to be talking about my research for all next week, the material that could appear on the final will end today, so I'm not going to require you to know anything from my research stuff. But so hopefully I'll get your final out maybe middle of next week, maybe Wednesday. That'll be a good day to get it out. Any last minute questions?
Is it final with all accurate, or is it?
I'm gonna probably make it either half and half or all all not hacker rank. So either half and half or all not hacker rank. Because from the midterm, it was pretty much at the limit of what hacker rank is anyway. And a lot of the problems in there rely on advanced mathematical techniques, which we didn't talk about here. And we did a lot more proof stuff, so there needs to be a component that's not on HackerRank. But essentially, yeah.
Sorry, I was just. Does that mean that how will we deal with what's not on the HackerRank? Are we just gonna come into class and sit down and just?
Oh no. So I'm gonna make it all available at the same time, and then you'll just type it up into PDF and then submit it. Yeah. With this material and the amount of material we covered, which is amazing actually, it doesn't make sense to have a timed exam. And it's actually pretty interesting with this field, what is called computational complexity theory. It's and I've been thinking about this a lot. It's a lot of the ideas used in it are basically only applicable most of the time to the same problem. Like some of the NP completeness reductions, we didn't use the same reduction for multiple problems. Like we had to develop a specific reduction for each of two choices of problems. So And like in a timed exam, what it usually comes down to is using previous techniques again for a new problem that you haven't seen before. So it's just using existing techniques. But here, you can't really do that. So it doesn't really make a lot of sense to have a timed exam. A really short timed exam, I mean. But because it requires you to be really clever in a short amount of time, which I don't believe is a good idea. And it stresses people out, and I don't like that. Okay, any other questions? Okay, I will see you next week.